So on this lecture, I will be generalizing our treatment from scalar valued waves into vector waves. So this won't be a long lecture, but nevertheless, this is highly useful because we all know that the light also has a property known as a polarization of light, and somehow we must develop our mathematical framework to be something that we can actually then describe also this polarization of light. So this is my motivation. And like I said, okay, so far we have been restricted in our treatment to scalar valued fields. And of course, in a way, this is nice because the treatment is simple, but this is bad because it doesn't really entirely correspond to the physical reality, because we haven't had so far tools to describe polarization of light. So this is the downside. So in essence, mathematically, our field amplitude so far has been a scalar valued quantity, and this is not nice. This is not what we want to have in the future. So we must generalize our scalar valued fields into vector fields and vector valued waves. And of course, the generalization is quite easy, so we do not need to do actually much. And I will just outline what is the result. I do not show the derivation. And in case the notation is not clear, most of the time I do not really differentiate between a scalar valued field and a vector valued field. But here I'm trying my best to highlight this fact that we are now actually changing, that our wave was psi, scalar valued psi before, now it's actually a vector valued psi. And here again, the arguments are whatever, so that we can have a wave propagating along an arbitrary direction. It oscillates with respect to time. But here, where the point why we have a vector valued function, the difference here is now that the amplitude A is no longer a scalar, but rather a vector A naught. The phase term is exactly the same as before, so we have a time harmonic plane wave propagating along the direction of wave vector k, but here is the difference that we are now introducing into our description. So instead of a scalar valued amplitude, we will now have a vector valued amplitude A naught. And this is the thing that makes my wave from a scalar quantity into a vector valued wave. In Cartesian coordinates, the vector valued amplitude can simply be written that A is the x coordinate along x direction, the y coordinate plus the z coordinate. And in a different notation, of course, this corresponds to a vector that looks like this. So we have the three components along x, y, and z directions. And out of simplicity, I'm just using Cartesian coordinate system to describe my physics. And here, each component, AIs, of course, they can be treated as a scalar valued field. So in principle, I could just have the same equation, wave equation as before, and I would now just describe my vector field, and I would just put it through the wave equation 3 times. So once for all these different components. The amplitude vector A of my electric field is actually called polarization of light. So like I said, the motivation in this generalization of the math comes from the fact that we do know that light is transverse electromagnetic radiation, and somehow it can oscillate along different directions. And somehow this is how nature works. This is electromagnetic radiation that we have, and subsequently the math should follow. So definitely we must be able to describe polarization of light somehow. And when we are considering a time harmonic electric field, and if it's propagating along the z-axis, the field will be of form that we have E, and this is a vector electric field, and depends on the coordinate z and t, and then the amplitude can now, the amplitude of the field can now be written that it's a transverse oscillation, so that we have only x and y components for my amplitude. And this complies with the fact that I have a propagating field along the z-axis, and like we know, electromagnetic radiation is transverse radiation, so it's oscillating on the plane transverse with respect to the propagation. So now with this, I'm ensuring that my polarization is really on the transverse plane. So there's no z component for a time harmonic plane wave. And then I have my phase evolution. So the phase function is kz times omega t. Sorry, kz minus omega t. So I can also simplify this notation slightly. So I can just take a kind of modulus of my polarization vector. So I can take the modulus of my vector valued amplitude, and that would be the E naught. And then I could write the rest of the vector information inside a unit length polarization vector P. And then the phase term will be unchanged. So here, of course, the E naught, that's the modulo square of my vector amplitude. So it's the square root of x squared plus y squared. And this is the scalar amplitude of the field. So it gives me the strength of the field, and this p hat, that's my polarization vector, and that gives me the actual information of how it actually oscillates, in which direction or in what way the field oscillates in that plane transverse to the direction of propagation. And this is known, this p vector here is known as the normalized polarization vector, or just shortly put, a polarization of light. So this is where we then have the information of how light actually oscillates in that plane transverse to the direction of propagation. So we have here this guy here as in before, and then we are adding this E naught here, and then we are like dividing the same E naught here, so then this equality holds. And why we did this is that we kind of like to have the polarization vector be a normalized vector, and hence the hat here, so that the amplitude information is not contained in the polarization, but rather the amplitude information of how strong of a field we have, it's a different number. And how the field oscillates, then that information is different from the actual amplitude. And now what we are left in this lecture is that I will be describing different polarization states, what kind of polarizations are out there when we are looking at different kind of fields. Well, the simplest of scenarios is a linear polarization. Please feel free to click on this link. It seems to be that there's something hidden underneath. So when you get the slides, please try clicking this. The field components Ex and Ey, in our case, when we have linear polarization, both of them can be written as a real valued scalars. And that's how we get linear polarization. So both of these X and Y components of my polarization oscillate at the same phase. I could also have a case known as a circular polarization. And in this case, I will have a phase difference of plus minus pi over 2 between the different components. So mathematically put, I can write my Ey component of polarization, that it's the exponent plus minus I pi divided by 2 times the Ex component. So in other way of saying, like I can write the exponent more simply as a plus minus imaginary unit, and the Ex remains unchanged. So this is a kind of way that we really see that now the different components, the Ex component and the Ey component of the polarization, they actually do have different phases with respect to each other. And the polarization vector, of course, will be a form that I have my p hat. It's 1 over square root of 2 and an x plus minus Iy hats. And now the interesting thing why it's called circular polarization is that depending either do I have a right-handed or so-called left-handed circular polarization, then the polarization vector rotates differently in that plane perpendicular to the direction of propagation. So we can have a right-handed circular polarization p hat r or er, and mathematically that's 1 over square root of 2, and inside the parentheses I will have x hat minus I y hat, and I can have left-handed circular polarization or E hat L, and this is the 1 over square root of 2, and inside parentheses x hat plus I y hat. And if you're interested in seeing how they actually do oscillate and rotate, please click on those links, right-handed or left-handed. They also seem to be having a link embedded in them, so that they hopefully you kind of get our points. What is the difference between linear polarization and circular polarization? And now finally, let's generalize. There's also a polarization known as elliptical. And this is, of course, the most general cases of polarizations. So there's actually an arbitrary phase difference between the different components Ex and Ey. So the ratio Ex versus Ey is an arbitrary complex number. And in general, of course, polarization of a field or more arbitrary field, it could also depend on the X and Y coordinates. So that that could also be a case, but this kind of treatment will be left for more advanced courses. So for plane waves, the polarization will be exactly the same in all these locations on the transverse plane, and it doesn't change. But in principle, it could also change. So one could imagine fields where the polarization vector depends on the location, but we do not go into that kind of extension here on this course. And I will conclude by just showing these different figures. Hopefully this helps for you to understand. So when we have linear polarization, the polarization oscillates only in a single plane. So the electromagnetic radiation oscillates along one line. Then in the circular polarization cases, the polarization vector rotates in the XY plane. And depending on the handedness of the rotation, we either call it left-handed or right-handed circular polarization. And the most general case, the Ex amplitude and the Ey amplitude may not be of the same length. And in addition, they may also have different phases. And then the oscillation will be elliptical in a way in that plane, perpendicular to the direction of propagation k. So this is what I wanted to say about vector waves. And essentially, I wanted to connect these vector-valued amplitude with the polarization of light, because sometimes this is exactly the kind of thing we must do in our mathematical treatment to understand the physics. So thanks, and please join me in the next lecture quickly. Thanks and bye-bye.